Welcome, chemistry students, to the next section. We are going to talk for a little while here about equilibrium. What is chemical equilibrium? It has to do with forward and reverse reactions. We're going to talk in this section about what it means, what the collision model of chemical reactions is. Here we have a nice collision. And very similarly, we're going to talk about that with chemistry and with chemical reactions. We're going to talk a little bit about rates of reactions, and finally give you the definition of chemical equilibrium and what that means. So first, let's look at the collision model of a chemical reaction. The collision model is just that. If we have this reaction, nitrogen monoxide, ozone, and it is creating nitrogen dioxide and oxygen, how is that happening? The collision model states that basically the two molecules collide and the energy, they bump into each other. The energy from that collision is great enough to break the oxygen-oxygen bond right here in the ozone, and it allows the oxygen-nitrogen bond to form. If you see here, this bond is breaking between two oxygens, and there is a bond here that is forming between an oxygen and a nitrogen, and that gives us our two products. We have some new terms to introduce. Homogeneous reactions or homogeneous reactions, however you like to say it, are reactions that involve only one phase. And remember what phases are: solid, liquid, gas. There's only one involved. A heterogeneous reaction would involve multiple phases. Reactants are in two phases at least. So here we have an example of that, of a heterogeneous reaction. It's zinc and hydrochloric acid mixed together. And if we look at that on this molecular level, we have the hydrogen ions that are aqueous, liquid, they're dissolved in the water, and they're coming in and reacting with this zinc solid zinc particles, and those are forming hydrogen gas and zinc chloride, which would be dissolved in the water. If we wrote it out, it would be zinc chloride, right? Aqueous. And this would be a heterogeneous reaction. One thing I'd like you to think about when we look at this reaction happening, what is affecting the rate of this reaction? What might you think about that could be affecting this? And you'd probably come up with something very similar to what we've studied so far. Remember when we talked about dissolving and the rates of dissolution? If we had more surface area, something could dissolve faster, right? Like the difference between a sugar cube and granulated sugar. The granulated sugar has a lot more surface area, so it dissolves faster. This also has a similar quality. The rate of this reaction is definitely affected by the surface area of the zinc. If we have a lot of zinc clustered together and clumped together with not much surface area, this reaction will proceed more slowly. Let's look at some other things that affect rates of reaction. If you'll remember when we talked about rates of dissolution, the rate at which a solute dissolves, temperature affected it, surface area affected it, stirring affected it. Well, we have some similar things that are affecting our rates of reaction. We have surface area again. You can tell that if you have, say, a clump of atoms or ions that are in here, the ones in the middle are not going to be able to react with these atoms on the outside. So if you would break this up and have more surface area, certainly that reaction would proceed at a higher rate. Concentration affects rates of reaction. Low concentration, if we talk about our collision model, we are not able to have as many collisions. There would be fewer numbers of atoms and we'd have fewer collisions. A high concentration, we would have more collisions. Same here with our collision model. There would be fewer collisions available to these atoms on the inside because of the surface area issue. Temperature. A similar thing, if we have a higher temperature, the molecules are traveling at greater velocities and you're going to get more collisions. They're going to bump into each other more often. And you can see this here. Here is the volume of a gas that is produced and the time of reaction. Well, the temperature at which it takes place, this is taking place at 100 degrees Celsius and this one at 75 degrees Celsius. So you can see that the reaction that is taking place at the higher temperature is proceeding faster at a higher rate. Also, the nature of the reactants themselves will affect the reaction rate. We can consider bond strengths, the structures of the molecules themselves. Those will also affect reaction rates. So now that we have looked at our collision model of a reaction and some different things that affect these reaction rates, let's look at what we mean by chemical equilibrium. And let's look at it by investigating vaporization and condensation. Vaporization, simply evaporation, we could also term this in this case. So here we have atoms being vaporized or evaporating from this solution, and those are indicated by the red up arrow. Molecules that are undergoing condensation are indicated by the blue down arrow. So these are vaporizing, and these blue ones are condensing. Here we have only vaporization being represented. This is only going one direction, up, right? They're vaporizing from the liquid to the gas phase. Here is a system showing vaporization rate up and a little bit of condensation rate. So there is some condensation happening also. We have more vaporization than condensation. So the vaporization rate is greater than the condensation rate. Now look in this system. Here we have a representation of vaporization being equal to the rate of condensation. So there is as much vaporization occurring as there is condensation. They are happening at the same rate. This is what we mean by chemical equilibrium. This is in a state of equilibrium because the rate of the forward reaction, or the rate of vaporization, is equal to the rate of condensation. In chemistry, when the rate of the forward reaction is equal to the rate of the reverse reaction, we are in chemical equilibrium. This would be considered chemical equilibrium. Chemical equilibrium can also be thought of as the dynamic state where concentrations of all of the reactants and products remain constant. At this point, we have everything that is in the gas phase and everything that is in the liquid phase. Those concentrations are going to remain constant because our rate of vaporization and rate of condensation are equal. So both of these statements are true. The dynamic state where the concentrations of the reactants and products remain constant is true because the rates of the forward and reverse reactions have reached equality and reached a state of equilibrium. Now let's take a look again at this reaction. We looked at it earlier. The zinc and the hydrochloric acid. This is a really neat reaction because it is a reaction, it is an equilibrium reaction. Goes both directions. And let's take a look at this. We have zinc and hydrochloric acid forming hydrogen gas and zinc chloride. But we also have hydrogen gas and zinc chloride forming just solid zinc and hydrochloric acid. So this is going two different directions. When we graph what is happening here, we can graph this in two different ways. First, let's look at the rate. And when we think about equilibrium and the fact that the rate of the forward reaction equals the rate of the reverse reaction, we're going to graph the rate of reaction versus time. And what we find is that when we start, our forward rate is very high rate. It's going fast because, in fact, that's all we have. We have our initial, we put the zinc and we put the hydrochloric acid together, we mix those together, and all we have is a really high reaction rate. We have high concentrations of both of these, and we don't have anything for the reverse rate because Initially, we don't have any product that is formed, so that reverse rate doesn't even exist yet. But it soon does, because as the forward reaction happens, it's producing some product. And we get the reverse rate increases because product is being formed, and then it can, in turn, produce more of the product, or more of the reactants, excuse me, and go in the reverse direction. So as the forward rate slightly decreases here, the reverse rate will increase until it reaches a point of equilibrium. Here we have equilibrium. The rates are equal. We have the forward rate equal to the reverse rate, and that is where we have achieved equilibrium. Another way we can think about it is to graph the amount of reactants and products versus time. In that case, again, we start with all reactants and no products, but as the product concentrations increase, the reactant concentrations decrease, we eventually get to a point where concentrations achieve equilibrium and they remain constant. There is not a change in this amount. It remains constant because this reaction is in equilibrium. And so those are two ways you can think about the state of equilibrium. So main points from this section: remember the collision model, the rates of reaction, what kinds of factors affect that, and chemical equilibrium. How do we define that and how do we think about that? Just one last point on that. Here's an example of an initial state and a state in equilibrium. Initially, we put bromine and hydrogen together. Here's the little key. Bromines are green and hydrogen molecules are this orangey color. Here is the equilibrium state. After some amount of time goes by and equilibrium is achieved, this is what it would look like. We're going to talk a little bit more about that in the next section, and about the process it goes through in achieving equilibrium. So advanced ideas, read some of these ideas. You're welcome to try any of them. If you have other questions or other things you want to look into, things that come up and you think would be really good, I'd love to hear your ideas, because I think sometimes you guys have really good questions that I just didn't think about. So please investigate those for advanced proficiency, and I look forward to seeing you in class.